In the last video, we introduced drag, and I would like to finish up this first pass at dynamics in one dimension with an integrated example involving both tension and friction. So the example I'm going to be thinking of is, imagine that you have a track like so, and we'll have a pulley attached to the end of our track like so, and as always here for the moment, we'll assume that our pulley is massless and that the strings attached to it are massless and don't stretch. All right, let's say that we've got a block. I'll call this mass 2 for reasons that'll make sense in a moment. Attached to a string, running over the pulley. And we have another block here. We'll say this is a 1 kilogram block here. Let's also assume that there is friction between these surfaces, and we'll assume that we can get this nudged fast enough to break static friction. So we'll say that we'll focus on kinetic friction here and say that the coefficient kinetic friction for these two surfaces is 0.2. All right, so we're going to take the sign and let it go. And what I want to know is, at what rate are these two blocks going to accelerate? First thing we'll note is that they will both be accelerated at the same rate, and this is because they'll both cover this, because the string doesn't stretch, they'll both cover the same amount of distance in the same amount of time. So they'll have the same velocity at all times, and the only way that can happen is if they have the same acceleration at all times. Okay, so let's go ahead and identify our systems here. So our two players here are going to be mass 1, which I'll note in red. So there's my force identification diagram started there. Mass 2 will do that in blue. All right, let's identify our forces. We've got, okay, the circle cuts through here, tension. We'll neglect air resistance because, as we saw in the previous video, that gets complicated fast. And our only long-range force is gravity. We'll call that FG1 for force of gravity acting on object number 1. And similarly, we can do a force identification diagram here. Now here, the circle will cut through the same string, and these two tension forces will be equal. We'll discuss that in a second. It also cuts through this surface here. And when it cuts through this surface, we'll pick up both a normal force and a force of kinetic friction, like so. And then we have a long-range force of gravity. We'll call that FG2. All right. Now, a quick observation here is that this red tension is equal to the blue tension force. And this is because it's the same string and we're assuming it's massless. So since it's massless, the stretch between the bonds for each adjacent molecule along the string, they'll all have the same stretch, and the tension is proportional to the stretch. So we'll just go ahead and assume that these two are equal here, which they will be as long as the string is massless and the pulley is massless. All right, let's go ahead and draw free body diagrams then. So for the red system, we'll have the force of gravity acting down, FG1, and we'll have tension acting up, like so. And I drew gravity longer than tension because I know from my common sense this thing's going to accelerate down, not up. That's also going to strongly suggest that I should choose down to be positive here in order to point the coordinate system along the direction of the acceleration so that I'm less likely to mess up signs. Okay, let's draw a free body diagram for the blue system. So for the blue system, we've got four forces acting on it. We've got force due to tension acting to the right. We have kinetic friction acting to the left, opposing the motion. And I drew it shorter than the force due to tension acting to the right because I know that the thing has to accelerate to the right if we're going to keep the string the same length. And then vertically, I will have the normal force and gravity, and I draw these the same length because they're the only forces that have any pieces vertically. And I know that the mass is neither levitating off the table nor is it crashing through the table. All right, so let's go ahead and write Newton's second law for each of these systems. I'll go ahead and start with the blue system first. So starting with the blue system first, I can say that F net equals M2A. So expressed as a vector sum, that will be N plus FG, FG2, my bad, FG2 plus T plus FK equals M2A. And we'll need to take both X and Y components of this. So what can we get out of this? For modeling friction, we'll need to know the normal force. So from experience, I know that it'll be faster if I do the land of Y first. And in the land of Y, all we have is the normal force up, gravity down, and that will equal M2A sub Y. But well, actually, let me just go ahead and ask, what is A sub Y equal to? Pause and get back with me. That's right, A sub Y here is equal to 0. Why do we know that? We know that because our acceleration vector points straight to the right. If it were anything other than 0, that would mean that it's either crashing through the table or flying off the table. So here, A sub Y is 0, which lets me set that term to 0. And I get that in this case, the normal force is equal to the force of gravity, which will be Fg2. So it'll be equal to M2G. All right, we'll tuck that away for when we need it. All right, we'll get back to modeling this, but let's just modeling the blue system, but let's just turn our attention to the red system for a moment and see what we can tease out of it. So our red system is going to be same deal, F net equals M1A, and that's tension plus Fg1 equals M1A. And we can go into the land of Y here. There's nothing happening in X, so we don't even need to bother here. And with me choosing Y positive downward, that's going to mean that Fg1 is positive, tension is negative, but since the acceleration points down, it means I can write M1A as a positive rather than a negative. All right, and we can put in our model of gravity here to get that M1 times G minus T equals M1A, and we have a problem. The problem here is that I want to find the acceleration, but I don't know the tension. Now, I didn't ask for the tension, but I got to get rid of it now somehow. And to do that, I need another equation that relates the tension, hopefully to things I know. Well, I haven't looked at the land of X in the blue system yet, so let's go ahead and do that. Land of X in the blue system, we've got the tension pointing to the right, kinetic friction pointing to the left. So, all right, T minus Fk, T positive because we're going to the right, Fk negative because we're going purely to the left, equals M2A. All right. Now, I can go ahead. It looks like I'm in trouble here because now, all right, I have an equation that has a T in it that I can put in to get rid of that T, But now I got this Fk. Well, I can go ahead and put in my model for kinetic friction. So that'll be T minus mu K, times N equals M2A. And I kind of go, oh fudge. That didn't seem to help at all because now I got a normal force I don't know. But then I go here and say, oh, in the land of Y, I already solved for the normal force and got that as M2G. So I can put that in for N. So finally I have T minus mu K times M2G equals M2A. I know this, I don't know that, but I can put it in here to make it go away there. Know this, great. I can now combine these. So you can do it however you like. In the last a few videos ago, I did this where I added the two equations. This time just to show that the world doesn't end if you do it differently. I will solve this one for t. You could totally add the two equations, and that's how I would probably do it, but just to do something different. I can solve this to get that t is equal to mu k m2g plus m2a. And I can take that result and put it in there. That will give me m1g minus mu k m2g minus m2a equals m1a. All right, so let's put everything with a's on one side and everything with g's on the other side. That'll give me m1 plus m2 times a equals m1 minus mu k m2 times g. Okay, and then finally, that will give me that the acceleration is m1 minus mu k m2 over m1 plus m2 g. Now, if you pause for a moment here, you realize that this looks vaguely familiar. It looks Atwood's machine-y. The only difference now is we've picked up this coefficient of kinetic friction in the result, which makes sense because now instead of us dealing with a force of gravity, it was a force of friction that happened to be proportional to a force of gravity. All right, well, in any event, we can go ahead and stick in our numbers. So we end up getting 1 kilogram minus, our mu k is 0.2 times 2 kilograms over 1 kilogram plus 2 kilograms times 9.8 newtons per kilogram. And I'm just going to immediately transform that to meters per second squared since I'm expecting to get an acceleration out. Punch this through your calculator, you get 1.96 meters per second squared. Alrighty then. In the next set of videos here, we're going to go ahead and start to take a look at Newton's third law of motion and see how that can help us to solve more problems. Catch you over there.